All right, so now we're going to move on to day 2 of section 9.2. Which is the law of cosines. Now, just like the law of sines, the law of cosines is designed to be used with non-right triangles. Again, it's not to say that you can't use it with right triangles, but the issue is that it's way more cumbersome and complicated to use than SOHCAHTOA. And if you have a right triangle, you can just use SOHCAHTOA, regular sine, cosine, tangent. If you have a non-right triangle, then you use law of cosines. So, law of cosines, just like law of sines, comes in 3 different flavors. So if we have some kind of triangle, I'll just put a generic triangle up here, and we have angle A, angle B, angle C, little a, little b, little c, the first version of law of cosines says that little a squared is equal to the other 2 sides squared and added together, so b squared plus c squared minus 2 times those 2 sides, b and c, times the cosine of the angle that goes with the side that was by itself over here. And this is the pattern for the other 2 versions. So we also have a version with b squared by itself. We also have a version with c squared by itself. The b squared version will be the other 2 sides squared and added together, so a squared plus c squared, minus 2 times those 2 sides, times the cosine of the angle opposite the side that was by itself. And then finally, c squared is going to be equal to a squared plus b squared. Looks like the Pythagorean theorem to begin with, but then we have this extra term, minus 2ab cosine of capital C. So this is your law of cosines. These are the 3 different versions. Bear with me 1 second here. So there we go. What we use this for is the same thing that we use law of sines for, and that is to solve triangles. So they're going to give you information, and they're going to ask you to find whatever information is missing in terms of lengths of sides or sizes of angles. So let's take a look at a couple of examples. The first example that we're going to take a look at, I'll go ahead and draw it like this. It's not meant to be drawn to scale necessarily. That'll work. And I'm going to put A up here, B here, C here. Then I have my little a, my little b, my little c. We're going to make angle B 120 degrees. We're going to make little c 7 centimeters. We're going to make little a 8 centimeters. So, measure of angle A equals measure of angle B equals measure of angle C equals. And then we have little a, little b, little c. We know that this guy is 7 centimeters. We know that this guy is 8 centimeters. We know that this one is 120 degrees. We need to find the 3 missing pieces of the triangle. So notice that what we are given here, going back to yesterday's lesson with law of sines and talking about congruent triangles from geometry, notice that we are given side, angle, side information here. And since side, angle, side was one of the theorems that we had to prove that triangles were congruent, that's enough information to guarantee us that there's only one possible outcome for this triangle. Okay, so we don't have to worry about the ambiguous case on side, angle, side. It's only angle, side, side that causes the ambiguous case. You're never going to use angle, side, side when you're dealing with law of cosines. Notice before I start law of cosines that we could not try and use law of sines on this even if we wanted to, because we don't know any of the opposite pairs. We either know the big one but not the little one, or the little one but not the big one. We have to know one opposite pair set in order to use law of sines. So there's no confusion when they give you three pieces of information as to whether you use law of sines or law of cosines. Only one of them will be an option. If you set up one of them and you're solving for two variables simultaneously, you set up the wrong one. All right, so let's go ahead and work through this. Notice that I was given angle B. Since I was given angle B, what I'm going to do is I'm going to use the version of this that uses angle B. It's the only one I can use because if I try and use the other ones, I'm going to be missing more than one variable. So we're going to use that little b squared is equal to a squared plus c squared minus 2ac cosine of b. We do not know little b, so that stays little b squared. We know that a is 8 squared plus c squared minus 2 times a times c times cosine of b, which is 120 degrees. Notice that's a unit circle value, so we're going to be able to get this without using our calculator. We can get an exact value for that. So let's go ahead and do this. We get b squared is equal to 8 squared is 64 plus 7 squared is 49 minus 2 times 8 times 7, well, that's 56 times 2 is 112, so minus 112 times cosine of 120. If you stop and think about 120, which is up there, our cosine value there is -1/2 from our unit circle. So this is times -1/2. So that gives us b squared equals, when I put these two together, I get 113 minus, but this is actually going to become a plus because we have -112 times -1/2, so plus half of 112, which is 56. So b squared is equal to 169, and so this one is very nice. B ends up being 13. So this came out to be a whole number for us, 13 centimeters. So there's one of the things that we needed to find. Okay, so go back and rewind that and replay that if you need to, if there's anything that didn't make any sense there. We're now going to move on and we're going to find our angles. Now, there's something that I want to talk to you guys about that can get a little bit tricky. Notice that we now have an opposite pair. We now have big B and little b, so we can now finish this using law of sines. On this particular problem, that will be safe. But on a lot of problems, that's not necessarily a safe way to go. But let's go ahead and finish this with law of sines to begin with, and then I'll talk about what's not safe about it. So I'm going to erase this just to move this little piece out of our way. So to finish this with law of sines, I'm going to have to use sine of b over b. I need to use my pair that I know, equals, and I can use sine of angle A over little a. I'm going to cross multiply. Actually, what I'm going to do is I'm just going to, well, let's cross multiply just to keep things consistent. So 8 times sine of 120 degrees is equal to 13 times sine of A. And then we'll divide both sides by 13. And so we get sine of A is equal to 8 times sine of 120 over 13. Problem is we're trying to solve for A. So how do we get rid of a sine that we don't want? To get just the angle, we take the inverse sine of both sides. And so A is going to be equal to inverse sine of 8 sine 120 degrees over 13. Let me make sure that I didn't run off the side of the screen on that and bring that back a little bit. We're now going to punch this into our calculator. So I pull up my calculator. I make sure I'm set to degrees, which I am. So I'm going to first punch in this inside stuff. 8 sine 120. Now 120 is a unit circle value, but we're going to be doing inverse sine of something that in the end will not be a unit circle value because of the 8 and the 13. So I'm going to go ahead and just punch that in and not use the square root of 3 over 2 for sine of 120 because it won't make a difference in my final answer. So I multiply those, I divide by 13. So that is my inside value. Notice it's less than 1, so I can do the inverse sine of it. And so now inverse sine of that answer gives me A is about equal to 32.2 degrees. And again, unless they specify otherwise, round everything to the nearest tenth. So this is 32.2 degrees. Now that I know two of my angles, all I have to do is add them together. So 120 plus 32.2 is 152.2. I subtract that from 180, which is going to give me 27.8 degrees. And there is the solution to our triangle. We have now solved it. So go back and rewatch that if you need to. If there's anything that you don't get, let it sink in. But I want to talk to you about why this is potentially dangerous on certain problems. On this problem, it was not dangerous. And the reason it wasn't dangerous was that this angle right here was obtuse. We talked yesterday about law of sines. And when we are dealing with law of sines, and in particular the angle side side case, we have the potential for the ambiguous case, where we might get a second triangle. Notice that even though I was given side angle side on this particular problem, what was it that I was actually using when I did law of sines right here? Well, I was using the 120 degrees. I was using the 8. And I was using the 13. Notice that is angle side side. I have now given rise to the ambiguous case. Even though the information that I started with in the problem does not create the ambiguous case, what I'm using here does. That leads us to a potential problem where in addition to my 32.2, I'd also have to do 180 minus that and see if it makes sense with the angle that they gave me. Now, because 180 minus 32.2 is obtuse, and 120 that they gave me in the original is also obtuse, if I add those together, it's going to be bigger than 180 guaranteed. And I can't have that, especially with only two angles. I haven't even looked at the third angle, and already I have too many degrees. So it's not dangerous on this problem. The issue is, what if this original angle had been 20 degrees? Well, then 180 minus this angle, which would be obtuse, added to 20 would give rise to a second triangle. The problem is only one of those two solutions would be correct. And I don't want to get into too many details about what would be incorrect about it, but what it would cause to happen, just in short, is that we would end up with a situation where, going back to geometry, remember that the biggest side always has to be across from the biggest angle. And the smallest side has to be across from the smallest angle, and the medium side across from the medium angle. If you use law of sines to finish this, and it turns out that you have created, in doing so, that ambiguous case, and you don't check for it and check and see which one makes sense, you may end up with a final solution where the biggest side is not necessarily across from the biggest angle, and then same thing with smallest and medium. That's the potential for the problem. So if you check for the ambiguous case and things like that, then you guys will be in good shape. And it won't be a problem for you. That's a lot to heap on your plate to try and remember, though. So let me show you the way that I would actually suggest that you do this instead. My suggestion to you is, instead of finishing these with law of sines, if you start with law of cosines, finish with law of cosines. So let's say I don't know. Well, actually, I'm going to, no, that's okay. I'm going to take this out, and I'm going to take this out. And I'm going to take this out. So this is what we started with, side angle side, no ambiguous case. We do law of cosines, and we get b equals 13. Now, instead of using law of sines to finish this, I'm going to instead use law of cosines again. So when I go to use law of cosines to finish this, let's say I want to find angle A. Doesn't matter whether I go for angle A first or angle B at this point. I could do either one. I'm going to go for angle A because that's what we solved for next just a few minutes ago. So now I've got to use the form of the law of cosines that uses capital A, angle A. So that means I'm now going to do A squared equals B squared plus C squared minus 2BC cosine of A. So A squared is 8 squared, sorry about that, equals B squared, there's my 13, plus C squared, there's my 7, minus 2 times 13 times 7 times cosine of angle A, which we don't know. That's what we're solving for, is angle A. So 64 is equal to 169 plus 49 minus, this is going to give me 2 times 13 times 7. 2 times 13 times 7 gives me 182 cosine of A. This is now 64 equals, this is now 218 minus 182 cosine of A. Now, here's where people mess these up. You've got to be very careful. You cannot do 218 minus 182 and get an answer of 36 cosine of A. These are not like terms. The 182 has a cosine attached to it. The 218 does not. So you cannot combine the right side into one term. What you've got to do is you've got to subtract 218 to the other side. So you get negative 182 cosine of A is equal to negative, and 218 minus 64, well, let's do 64 minus 218 so that we see we get our negative 154. Now we're going to divide by negative 182 on both sides. And so we get cosine of A is equal to, so negative 154 divided by negative 182 gives us this value. So 0.846 dot, dot, dot. I'm not going to write the whole thing down. I'm going to leave it in my calculator. And what are we now going to do to solve for A? We're going to do that angle A is equal to the inverse cosine of that 0.846 dot, dot, dot number that's sitting in my calculator. So now I take this number and I do inverse cosine of that answer, and I get 32.2 degrees. Notice, it gave me the same answer that we got with law of sines. The difference is there's no chance of this one giving rise to an ambiguous case. And so I don't have to worry about running a reality check on my final answers necessarily to check and make sure that the biggest side is across from the biggest angle, etc. I don't run the risk of getting the wrong possible triangle as my answer. And so my recommendation, even though this is not the way most teachers teach it where you use law of cosines the first time and then you use law of sines after that. That's great when the angle they gave you originally in the original problem was obtuse. No danger whatsoever. If it's acute, you run into potential for danger. So my recommendation, when you use law of cosines to start a problem, use law of cosines all the way through it, and you can completely avoid that pitfall. All right, so that's our example. The other example that I want to do for you is similar to this one, but I'll do one more example. I want to do the side-side-side example for you. So this time, we have a triangle. Again, I'm just going to make it as a generic triangle. It's not meant to be drawn to scale. And this is going to be 3 and 5 and 7. Notice we have side, side, side this time. That also is something that we can use. It's actually a postulate rather than a theorem in geometry in most books. But it allows us to prove that two triangles are congruent to each other. It guarantees there's only one shape of triangle we can have, no ambiguous case. I'm going to call this A. I'm going to call this B. I'm going to call this C. So this is little a, little b, little c. Notice, well here, let me put these in first. Measure of angle A, measure of angle B, measure of angle C. Little a, little b, little c. Notice that we have little a is 3, little b is 5, little c is 7. We are missing all 3 angles. Notice we don't have any opposite pair where we know the angle and its opposite side. So law of sines is not even an option here. So we're going to go ahead and solve this. It is up to you which of these angles you look for first. I'm going to go in alphabetical order. I'm going to find the measure of angle A first, which means I need to go back here and I need to use the one that has capital A in it, since that's what I'm trying to solve for. So we know that little a squared is equal to b squared plus c squared minus 2bc cosine of A. So I have 3 squared equals 5 squared plus 7 squared minus 2, 5, 7 cosine of A, which is what we're solving for. So 9 equals 25 plus 49 minus 70 cosine of A. 9 is equal to 60, 74 minus 70 cosine of A. Here's that same danger issue that we talked about on the last problem. You cannot do 74 minus 70. These are not like terms. So you subtract 74. So negative 65 is equal to negative 70 cosine of A. Divide by negative 70 to get cosine by itself. And you get cosine of A is equal to negative 65 divided by negative 70 is going to give you 0.92857 dot dot dot, 0.928 dot dot dot. And so A then is equal to the inverse cosine of that 0.928 dot 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 number that I'm leaving in my calculator, which I then punch into my calculator. Second function cosine of the answer, 21.8 degrees when we round it off. So this is 21.8 degrees. Now going back to what I said the last time, notice, guys, that we now have an opposite pair of angle and side. We could now use law of sines to finish this. The problem is that the angle that we know is acute, and that's going to give rise to the ambiguous case with 2 possible triangles to finish this with, only one of which is right. The other one is absolutely wrong. Okay, so rather than run that risk, I'm just going to finish this with law of cosines again. I'm going to find angle B now. So I'm going to use little b squared equals a squared plus c squared minus 2ac cosine of B. So 5 squared equals 3 squared plus 7 squared minus 2, 3, 7 cosine of B. 25 equals 9 plus 49 minus 42 cosine of B. 25 equals 58 minus 42 cosine of B. Again, I cannot combine these, so I have to subtract this to the other side. So negative 33 equals negative 42 cosine of B. So cosine of B is equal to negative 33 over negative 42. Negative 33 divided by negative 42. It's 0.785 dot dot dot. And so B is equal to inverse cosine of that number. And when we punch that into our calculator, inverse cosine of the previous answer, we get 38.2 degrees. And now I can just add these together, 20 and 30, 50, 9, 60. Those add up to 60 degrees. Subtract from 180, leaves me 120 degrees for my final angle. So I don't have to do it a third time. I can just do it twice. Notice that I ended up with the smallest side across from the smallest angle, the biggest side across from the biggest angle. So that all makes sense. And I didn't have to deal with the ambiguous case in the process and run the risk of getting my answers wrong. So again, if you are forced to start the problem with law of cosines, my recommendation to you is you should also finish the problem with law of cosines. Use it twice rather than doing law of cosines and then law of sines. So that's the lesson. There are other examples in the book, I believe, for you to take a look at. And you can go ahead and check the calendar and get started on the assignment.